Hello everyone and welcome to this video. So we are now officially starting with this playlist of O-level electricity, and this is going to cover some or most of the ideas discussed in electricity. This is the first video on that, and we're starting from the very basics, talking about an important idea, which is that of the electric current, right? So first of all, before this chapter, you must have studied the chapter of static electricity, and you must have studied something called charge. Now, why was that chapter called static electricity? Is because the charge was not moving, but when the charge does start to move in any shape or form, that leads to current, right? So formally defining this, you can say that current is defined as the rate of flow of charge, right? So this is the official definition. If the examiner ever asks for it, this is what you would say. Now remember that these type of definitions where you say rate of something, so for example the rate of flow of charge, this is something that you've also seen way back in the chapter of kinematics. So what this means is this can give you a possible idea of what the definition is like. So I can say that current I is basically the rate of flow of charge, so that is the charge flowing in some time, right? So rate always means that in the formula of something, the denominator is going to have time in it as well. So rate of flow of charge is change in charge over change in time. So this is the defining equation. Again, I've just written I equals delta Q over delta T here because technically that is what it is. But in O levels, the examiner won't really care a lot about deltas here. So you can also write it as I equals Q over T, or rearranging, you can also say that Q equals I T, right? So current, when we talk about this as an idea, so first of all, current is a scalar quantity. So that means that direction does not matter with current, and this is measured in the SI units of amperes, the symbol for which is capital A. Another important idea that we need to understand here is that when we talk about current, then remember that when you were studying static electricity, so you must have studied charging by rubbing or charging by friction, in which case you always know that it's the electrons which are transferred. Similarly, when we talk about current as well, so current is due to movement of charge. Yes, that is true, but from a particle point of view, that is due to the flow of electrons, right? So it's not the protons, it's not the neutrons which carry current, it's because of the electrons that current flows, right? So when we say charge flows, it's basically because of electrons, and we know the reason for this as well, because the electrons are loosely held in the orbit and they participate in the flow of current, whereas the protons and the neutrons which are in the nucleus do not, right? So also remember this, that you must have studied in the previous chapter that the charge of an electron, that is given by 1.60 into 10 to the negative 19 coulomb. This is not a value you need to know, but you do need to know that it has some charge, and the idea is that there can be no smaller charge than this. So the idea that then follows through is this, is that the any charge that we are talking about, so all charge must be an integer multiple, of the charge of an electron, which is also, by the way, called fundamental charge, right? So what I mean by this is writing this in the form of an equation. If I have some total charge, so that is the number of electrons multiplied by the charge of one electron, right? So for example, if one electron has a charge of this much, two electrons would have twice as much charge, which would mean 3.2 into 10 to the negative 19. 3 would have thrice as much charge, which would become 4.8 into 10 to the negative 19, and so on. And this is all that this equation says. In AS, we also call this equation, we call this the quantization of charge. And this just means that charge occurs in discrete quantities. So for example, charge, if we talk about it, it could be 1.6 into 10 to the negative 19 or 3.2 into 10 to the negative 19. But since there can't be like a half of an electron or a quarter of an electron, so it won't be any value in between. So all charge must be integer multiples of the charge of an electron. Now let's do a quick example to see what we mean by this. So this is the example, a charge of 750 millicoulomb, by the way small m is milli, coulomb, passes a point in a time of 2.5 seconds. Find in part A the current flowing at that point. So part A, if we need to find the current, so current is just the rate of flow of charge. So we'll use the equation that we just wrote down, delta Q over delta T. This is 750 milli, so milli means 10 to the power of negative 3 divided by the time, which is 2.5 seconds. If you work this out, the answer would turn out to be 0.3 amperes. So to write this to a minimum of 2 SF, this is how you can write it. Part B, the number of electrons passing the point. So when we talk about the number of electrons, we can use this equation that we just saw, that the charge must be an integer multiple of the number of electrons. And don't worry, because the charge of the electron, this would also be given to you. So charge of an electron, this is given to you in the question, 1.60 into 10 to the negative 19 coulombs, right? So this is given. Now we just need to work out n, the number of electrons, which is Q over E. So 750 into 10 to the negative 3 over 1.60 into 10 to the negative 19. And when we work this out, this turns out to be 4.6 into 10 to the 18. Obviously, this is the number of electrons, so this has no units as such. Now, when we talk about what current really is, so we've seen the formula for a bit, but it's also important to understand the ideas, because the ideas are what will also link up later to other quantities. So let's say I make a very simple circuit diagram, and with the circuit diagrams you also have to get used to the circuit symbols. So this that I've drawn here is the circuit symbol for a cell. I'll also explain that in a while. These are connecting wires, these lines that are there. So like this. And that is connected to a cylindrical piece of metal like this. This can be thought of as a metal wire. So let's talk about the circuit symbols first. This is a cell. The longer end is the positive end, the shorter end is the negative end. For example, even if you're inserting batteries into a remote control, you see these positive and negative of the cell. This is basically that. All of these solid wires, they are called connecting wires. And what I've just drawn is basically a piece of metal. Now what we know about this piece of metal is that being a metal, it has something that we call our free electrons, right? So let's say that there are a lot of free electrons here in this metal. And we know that for a metal, the electrons are free. So they're delocalized and they can move in different, they're not restricted to any certain space. So they can move within the structure of the metal. And let's say this is what this looks like, right? So that's not something which is new to us. But then when connected to the cell, it does something that it gradually causes the electrons to, the technical term for it is that it causes the electrons to drift from one end to another. And let's talk about how this happens. So the cell has these terminals, and we just said that the flow of current happens due to electrons. So one way to think about this is that the negative end has an excess of electrons and the positive end has a deficiency of electrons. So with the negative ends having this excess of electrons, it causes the electrons to enter into the circuit, and this causes all of these to drift gradually from one end to another. And you can also think about it this way, that because these electrons are negative and these are also negative, they'll cause them to be repelled and move all the way to the other end. Because we know this from static electricity, that like charges repel, unlike charges attract. So these electrons are gradually attracted towards the positive end of the cell, and this is how the current can be thought of as flowing. So what I've marked here is basically what's called electron flow. And as we can see, electron flow is happening from the negative terminal of the cell to the positive terminal of the cell, as should happen from the place where the electrons are more to the place where electrons are less. However, the problem that happens when we talk about electric circuits is that we actually discovered the current way before we actually came across the electron. And at that time, when people saw current, they thought that it's basically happening because of the flow of some positive charge. Something we now know is not true. So they thought that positive charge goes out of the positive end and through into the negative end. Right? This is what that people thought at that time. This is what is called conventional current. So by that obviously incorrect convention that was there at that time, this is just how we talk about current. So we say that naturally current conventionally flows from positive to negative, even though in reality it's the electrons which take it from negative to positive. One last thing that we'll be talking about regarding current before moving on is one possible categorization of currents. So we can split currents into two categories. The first one we'll call direct current. Now what's direct current? Direct current is basically current that flows in one direction only. So technically we can say that it's unidirectional. So something to keep in mind here, because the examiner does sometimes test it, is that the value for direct current is mostly constant. For example, when you charge your laptops or when you charge your phones, that is being charged on direct current, and most of the time it happens that it provides a fixed value of the current, but the value of the current being constant is not really a requirement. As long as it is in that same direction, even if the value changes, we would classify that as a direct current. Now to understand what I mean by this here, we need a couple of graphs, so let's get those. So these are a couple of current versus time graphs to demonstrate the idea of something being direct current. So direct current means that it's always in the same direction. So for example, I can think of it this way, that let's say current to the right is positive and current to the left is negative, right? So let's say if I have a value like this, and let's say that the actual value in numbers is 5 amperes, this is a direct current. So its value is also fixed, it's not changing, and its positive means it's flowing from left to right. That means the direction is the same. Similarly, if I have another value of the current, let's say a value like this, which is minus 3 amperes, this is also direct current, because the minus sign basically shows that it's flowing from right to left now, and the value is constant. Again, the value being constant is not a requirement. As long as it remains either all negative or all positive, this is direct current. So even if I had a value like this, so something like this would also classify as direct current. So all of these three examples are direct current because they keep flowing in the same direction. In this one, the value may be changing, but because it stays all positive throughout, so the current keeps flowing from left to right. And now what's the opposite of this? The opposite of this is what we call alternating current. So what's alternating current now? Obviously, if direct current was always flowing in that same direction, for alternating current, the current flows in both directions, right? So sometimes it's flowing in one direction, and after some time it starts to flow in another direction, right? For example, the electricity supply that we get from the sockets in walls, that's alternating current, right? You might have seen a lot of appliances marked like, for example, they might be marked like 220 volts, 50 hertz. So that 50 hertz basically shows you that frequency, because now you've studied waves. So it shows you that frequency with which the wave shape is repeating. So how it repeats, it sometimes flows in one direction, then it flows in opposite direction. Again, let's have the graphs back here. So we have the same graph shapes here again. One of the most common alternating current shapes that we have is this. This is what we actually have in our homes. And the 50 hertz basically means you have 50 of such waves coming in. And because now you also know the formula that links frequency to time period, this is basically one shape that keeps repeating again and again. So 1 over 50, which I think is 0.02 seconds, gives you the time period of one of these waves. Similarly, another one which is pretty common is this. And these are all examples. You don't need to know these, by the way. I'm just showing you why they're AC. This is called a square wave. Another common one in electronics is this, which is called a sawtooth wave. Now for these, you see that these are sometimes positive, sometimes negative, which means current sometimes flows from left to right and other times it flows from right to left, which is why this is AC. So that was just a little bit about alternating currents. In the next videos, we'll be looking at more ideas now related to EMF and potential difference. See you there.